today is lecture 16. We're going to continue chapter 9. So in gas power cycle, we started with some assumptions about we're going to assume it's air, everything is reversible. We give the first cycle, which is, we give two cycles, Carnot, which we gave you before, then we give Otto cycle. And Otto cycle was 4-stroke piston cylinder engine. It has mainly two strokes we discuss, and they are two isentropic and two constant volume. So here isentropic, and two constant volume in the PV diagram. In the TS diagram, which is always better, they are something like this. So we have here two isentropic. This is 1, 2, 3, 4, 2, 3, 4. This is V equal constant, and this is V equal constant. So from 1 to 2, we have isentropic, constant entropy. So we can use isentropic relation between 1 and 2. So for 1 or 2 or 3 or 4, we can use ideal gas law, PV equal RT. If it's air, if it's other fluid, so this R based on the fluid. If it's air, for example, use table A to A. If it's R134A, carbon dioxide, whatever, use table A to A. The same for between this and this. For 1 and 2, for example, it's isentropic. It means T2 over T1 equal V1 over V2 to the K minus 1. This is the relation between 1 and 2. Isentropic relation. Do you remember when I said P inverse proportional with the V to the K and P proportional to the T over K minus 1? Combine them together, you can get this one. So T inverse with V to the K minus 1. Between 2 and 3, constant volume. For example, 2 PV equal RT. 3 PV equal RT. If you divide, you can say just P2 over P3 equal T2 over T3, because V2 equal V3, and so on. This was Otto cycle, and we said that we have here Q high. This is VV, this is Q high, this is Q low, this is work done. Net, actually this is out, and this is in. Subtraction give you the net work. Okay guys, any question? Any question? The whole idea here, we have compression. You have the burning, the heat in and heat out at constant volume. Very clear here, constant volume. This is Otto cycle. The heat addition and heat rejection were at constant volume. Let's now talk about 9.6. The next section, which is 9.6. So today is lecture 16, August 5th. We have 9.6, which is diesel engine. Again, these are designs. Everyone has concept in his design. We'll say what the difference is. So diesel engine, exactly same as Otto engine, except that we have heat addition at constant pressure. So let's plot the PV diagram or TS diagram. TS diagram of diesel engine. So pressure, specific volume, or temperature, entropy. Here we start, I said before, here, bottom right. Here I started here, bottom left. This is 1, set 1, set 2. State 1, we have isentropic compression, like this. There is no heat addition, it's reversible. Let's say this is 2. Here we have this. So this is isentropic. Isentropic means delta S equals 0. This is isentropic. So between 1 and 2, use isentropic. Exactly same as Otto. So the piston going up isentropically. It means P V to the K equal constant between two states. Isentropic between two states. Here ideal gas law, here ideal gas law. But between two states, isentropic. When I burn, unlike the Otto cycle, I burn at constant volume. Assume it's fixed volume, I burn. No, here, constant pressure. So that's the difference. So in Otto, we go vertically. In diesel, we go horizontally. Constant pressure. Otto, constant volume between 2 and 3. The heat addition was at constant pressure. So here, we have constant pressure. So it was volume equal constant in Otto. Here is constant pressure. Then we're gonna expand. The piston will go down, give you the power. So we're gonna get power at constant isentropic, which is no heat addition, no irreversibility until 4. Then we have heat rejection. So we have isentropic work, then heat rejection. So Q low, this is Q high. Anything has Q, it's not isentropic, of course. Entropy increases with heat. Entropy to be isentropic need to two things. To have any isentropic, you have two things. Adiabatic plus reversible. Everything is reversible. If you have adiabatic plus it's reversible, it means isentropic. Like works, turbine, pump, compressor. But if you have heat rejection or heat addition, this line and this line, like boiler, combustion chamber, condenser, all these components, heat addition or rejection. It means non-adiabatic. So we have either constant pressure or constant volume, or sometimes constant temperature, like Carnot cycle. So here, the heat addition at exactly same as the other one, but the Otto was V equal constant. Here, pressure equal constant at heat addition. Any question, guys? Any question, guys? Guys, any question? Everything is clear? So we start from bottom right. Here, bottom left here. That's all in TS diagram. Guys, can you hear me? Everything is clear?
Yeah.
Yes.
Everything is clear? So Otto, we move vertically here, constant volume, and go down. Diesel, horizontal, and heat addition. Any question, guys? So if you open with me lecture 16, I send you some notes. So open them, you will see what is going on in the comparison. So in this part, the piston moves to somehow keep the pressure always constant, almost constant. So guys, temperature here is higher or here? Which one temperature higher, 2 or 3? I added heat.
At 2.
I added heat. I added heat. So pressure is constant. Remember always PV equal RT. Pressure is constant. If the volume increases, temperature increases. So volume increases. Now we're going to define new ratio. So we have, I did kind of mistake last time. R is a compression ratio, not RC. I fixed it in the lecture. R is V2 over V, actually V1 over V2. V big maximum over V small. The maximum volume over minimum volume. From bottom dead end to the top dead end. So V max over V min. There is another something in between new is called V3. We call it RC, cut off volume ratio, which is RC V3 over V2. It's greater than 1, but still. So if RC became 1, this point became here. It means the ratio between V3 and V2 equal 1. It became Otto cycle. Okay, guys? So RC, a cutoff volume ratio we have now. If we move from 2 to 3 vertically, Otto. If we move horizontally, diesel. Okay, guys? Is it clear? Is it clear, guys?
Yeah, and for the second graph, that's for the isotropic case, right?
They are the same curves. One we plot in the PV diagram, one we plot in the TS diagram.
All right, thanks.
They are the same. It means this is the same cycle. We start from 1, P1, V1, T1, S1, and so on. And here P2, T2, S2, V2, H2, whatever. The same here. P3, V3, T3, H3, everything property here. But this is ideal gas, there is no quality. The same for 4. Here the same thing. P1, V1, T1, S1. So this point, exactly this point. This point, exactly this point. 1 to 2 isentropic. It means here like this in PP diagram, here like that in TS diagram. It's constant entropy. S2 equal S1. S2 equal S1. The better thing is to use P V to the K equal constant. This is a simplified form. If you remember, delta S was CV ln T2 over T1 plus R ln, I don't know, V2 over V1 or the other form. If you put delta S equal to 0, you got this equation. Do you remember, guys, something like that? So this delta S for ideal gases. So this is the isentropic relation, which is correct if you have two states and there is isentropic relation between them. Okay? Okay, guys, any question? So these are the same curves. I can ask you to plot this or this. So here, let's talk about the processes. As you can see, 1 to 2 is isentropic compression. Compression means volume decreases, pressure increases. Yes, volume decreasing and pressure increasing. Isentropic compression. Isentropic means like P V to the K equal constant. Like for example, P1 over P2 equal T2 over T1 to the power K over K minus 1. Or T2 over T1 equal V1 over V2 to the K1 K minus 1. The same and so on. This is called isentropic relation between 1 and 2. Between 1 and 2. There is no heat addition. It's adiabatic and reversible. That's why you call it isentropic. 2 to 3, heat addition at constant pressure. Heat addition at constant pressure. It means the piston free to move at constant pressure. So 2 to 3, heat addition at constant pressure. So this is closed volume. So Q minus W equal delta U. Because it's constant pressure, you can use this, or Q equal delta H. How many? Don't forget, remember this. At constant pressure, either Q minus W equal delta U, because the pressure, the work is PDV. Because it's constant pressure. The work, if you go to the simplified form, W was integration, P delta V, a pressure constant, which is this case, so just P delta V. So PDV give you the work here. Take it the other side, double delta U plus PDV, it means delta H. That is the definition of enthalpy. So both are correct. Either Q equal delta U plus W, Q equal delta A. Which one is better, guys? Which one is better? The first or the second? Which one is easier? Q minus W equal delta U or Q equal delta H?
The Q equals H?
Exactly, changing the entropy. That's exactly easier. Let's talk about periodic masses. So do you remember for ideal gas what delta H is? Somebody tell me what is periodic mass? Delta H is what? For ideal gas. If we assume the heat capacity at constant pressure is constant. So what is this?
H1 minus H2.
Which is what in ideal gas? This is gas, ideal gas. Everything here, gas, power engines. Delta H. So ideal gas. We said we have two things. We have ideal gas, we have steam table. Ideal gas, like PV equal ID. You have two ways to solve a problem. Ideal gas, and we have steam table. We don't have any steam table now. The only cycle have steam table, Rankine. Forget about it now. Ideal gases. You have PV equal RT. You have kind of isotopic relation like this. You have U equals CVT, H CPT. So if you want in a delta S equal CV ln T2 over T1 plus R ln V2 over. So if you want to get delta U, delta H, P, like if you have, for example, V and T, you can get P, you can get U, you can get H, you can get S. So you can get all the properties if it's ideal gas. So for here, Q equal what?
CP times T2 minus T1.
Exactly, delta T, T2 minus T1. This is Q hard. That's it. So if you remember in Otto cycle, we said 2 to 3 was constant volume. Constant volume, there is no work. That's why it's a Q equal delta U. And delta U was CV delta T. So in Otto cycle, 2 to 3 was constant volume. That's why Q minus W became only delta U, which is this is 0 because it's constant volume, rigid tank. The piston doesn't move. It's constant trapped air. There is no work. So Q equal delta U, which is CV delta T. That's why we did that. So ideal gas, do not forget this. From two independent intensive properties, you can get everything. Okay? Okay, guys? Usually P and T, P and V, so you can get the rest.
Professor, by the 2 to 3, it says heat addition, what?
At constant pressure.
Okay, thank you.
Oh, you're talking about the text here? Oh, sorry. This is at constant pressure. So this is a heat addition at constant pressure, horizontal. It's given in lecture 16. If you open with me lecture 16, you will see that I mentioned the steps. Did I? I think so. No, I did not mention the steps. I mentioned it for other one, but I mentioned the curve. So how about 3 to 4? What is this, guys? The power. So here we have some confusion. This power, actually we have two powers. Power from here and power from there. So power here is input from 1 to 2 because we compress, we pay something. So that's, let's say this is what I pay. This is what I get. So the difference between this is the net. So remember, when we talk about W net out, it's actually W between 3 and 4 minus W 1, 2. So 1, 2, we have compression, we pay something. We need to subtract it, which is equal Q high minus Q low. Q high minus Q low. This is W net out. So we usually easier we use this way to get W net. We don't use this much. We use usually Q high, which is again process. Always heat with a process. Unlike properties, it's associated with a state. That's ABC thermodynamics. So W net, which is this minus this, is equal Q high minus Q low. Exactly like what we did in chapter 6. Okay, guys? So isentropic means you can use between this point and this point isentropic relations like this. Okay, guys? That means P3 over P4 equal T3. Actually, this is proportional. This is 1. I'm sorry, this is 2. So 3 over 4, 3 over 4 to the Q cube. 2 over 1, no, he 1 over 2. So 3 over 4 equal 4 over 3. V4 over V3 to the K minus 1. So this one isentropic, 3 to 4, 1 to 2 is also isentropic. Okay, guys? So 3 to 4 is isentropic expansion or power. It's power stage, power stroke. This is where we got work or power to rotate the shaft. 4 to 1, heat, rejection, at constant what, guys? Constant what? Pressure or volume?
Volume.
Volume. Exactly same as? Same as? What cycle? What cycle? Heat, rejection, at constant volume. Which one? Same as what? Otto cycle. Same as Otto cycle. So Q minus W equal delta U. There is no W because constant volume. So just Q equal delta U. Which is mean what? Which is what here, guys? If I want delta U for ideal gas, what is this? What is this, guys? For ideal gas, what delta U? Guys, what?
CP.
CV.
CV, sorry.
CP is for enthalpy. CV for internal energy. We discussed this many times when we talk about ideal gas in chapter 3. Okay, let's now derive the so we define two volume ratio, V2 over V1 and V3 over V2. Actually, V1 over V2, which is VRR, and V3 over V2, which is RC. We have two ratios. How about the thermal efficiency? So thermal efficiency here can be derived. So thermal efficiency of O2, we get 1 minus Q low over Q high, and when simplified, it was finally 1 minus over R, which is compression ratio, to the power 1 or K minus 1, something like that. Do you remember, guys? This was for O2 cycle. This is the last thing we did in the last lecture. So it was CV delta T, CV over delta T, then we simplify. Do you want to repeat it, guys? Repeat this part?
Yeah, could you please?
Yeah, sure. I can redrive it for you, no problem. I did it in lecture, but I can do it again. Look at this. So Otto cycle, guys, the heat addition and rejection at constant volume. So if you plot this, this was vertical, this was vertical. Heat addition or heat rejection at constant volume. That's why we can say Q high was C. This is Otto cycle. Q high CV delta T, which is T2 minus T1, T3 minus T2. Q low, which is 4 to 1, was CV delta T. T high minus T low, T high minus T low, like this. Why CV? Because both of them at constant volume. Both of them delta U. There is no work. So plot like this. Heat addition at constant volume, heat rejection at constant volume, vertically in PV diagram. This is Otto cycle. Eta thermal was 1 minus Q low over Q high, which is 1 minus CV T3 T4 minus T1 over CV T3 minus T2. Which is 1 minus CV cancel CV, take T1 common factor, take T2 common factor. Everything is clear, guys?
Yeah.
So remember, V2 equal V3, V1 equal V4. 2 and 1 isentropic, 3 and 4 isentropic. This will lead to, if you want, stop here 1 second. We have V1 equal V4 and V2 equal V3. That's for Otto cycle. Yes. And 1 and 2 isentropic. It means T1 over T2 equal V2 over V1 to the K minus 1. 3 to 4, but also isentropic. So we have T3 over T4 equal V4 over V3 to the K minus 1. This is 1 over R. This is R. So this equal 1 over this. So T3, correct? T3 over T4 equal T2 over T1. So T3 over T2 equal T4 over T1. Oh, so this term is exactly this term. So this is 1 over R. V2 over V1 is 1 over R. Compression ratio. V4 over V3 is R. So if you want, write T4 over T3. So here will be V3 over V4. So this is R, and this is 1 over R, 1 over R. So this equals that. Rearrange, so you can say T3 over T2 equal T4 over T1. How about 1 and 2? 1 and 2, 1 over 2, which is this ratio, it's 1 over R to the K minus 1. So I can replace this by 1 over R to the K minus 1. It means eta thermal equal 1 minus 1 over R to the K minus 1. Is it clear, guys? Guys, what's going on? Is it that hard? That's so simple. Otto cycle, we have 4 processes. 1, 2, isentropic. 2, 3, heat addition constant volume. 3 to 4, heat work power. Then heat rejection. The same as this one. 1, 2. Actually, I like this better. Isentropic, constant volume, isentropic, constant volume. Heat addition, heat rejection. Guys, is it clear? If it is not clear, I don't like to not have answer for both sides. Clear or not clear? If it's not clear, say it's not clear. I can repeat it differently.
It's clear.
So for any other guys, is it not clear for you? Please say it now. I can say it again differently.
So the value of R is the compression ratio.
Perfect. PV
Correct.
max over V min, which we wish to be infinity to reach 100% efficiency, which we cannot. If the efficiency, this ratio is infinity, this is so big and this is so small, we can have the maximum thermal efficiency for Otto cycle, correct?
Yeah.
If we put limit R tends to infinity, this will be 100%, which is impossible. It's V max over V min, V max over Vn, V max over V min, V1 over V2. Okay? Okay? So let's
Yep.
repeat the same thing for what? For diesel. For diesel engine or diesel cycle. Do you want to watch a movie now before we go?
Yep.
Yeah. Home Alone? Wanna watch? So I see a lot of questions, but they are all about the My Beautiful Handwriting. Okay. So we were talking about diesel. Which one I was watching? I think this one. Yes. Okay. So let's watch these guys together. Can you see and hear, guys?
Yeah, we can see.
So he first give all the names of all the components, parts. We care about the piston, the crankshaft, the piston here, and the cylinder. This is a cylinder, this is a piston, and this is a crankshaft, which is gonna spin because of this movement. This linear movement will be rotational movement due to this design, which is called crankshaft. We have here intake. We have here exhaust, and this is fuel. He will describe now stage by stage what will happen when it is open. This camshaft is a very beautiful design. If it spin, it's gonna keep it closed until it touch this point. We will keep it open at one phase. Like if you have four phases, 4 quarters, only one quarter will be open. The rest is gonna be closed. The same for this one. They are shifted by 45 degrees to make one open, one close, one close, one. This is called cam shaft. CAMSHAFT. Cam shaft. Open. And if it's 4 quarters, open and 1 quarter, closes the rest of the quarters. Okay, let's see it. So the right valve is closed. However, it's spinning, while the left one is opening now. So this is the important part. We can move now. Gonna compress the fluid, which is stage 1. 1 to 2. we care about compression, then heat addition, then expansion, heat rejection. So unlike Otto cycle, which has a spark plug to create the ignition, we have self-ignition here. It means due to the high compression of the air and the fuel, there is self-ignition. It means that the spark started by natural higher temperature of the air. So, however, we did not discuss much about intake and exhaust stages in our analysis. So naturally, we have 4 strokes. We care about compression, heat addition, power, and heat rejection. But we neglect the intake and exhaust because these are open system, will add complexity to the system. So we talk about closed system, assume it's air, everything is reversible, everything is pure, ideal. But naturally, it's not. That's not correct. And we have extra 2 stages. If you remember, we said we have intake and exhaust. Now, as you can see, as I told you before, the good thing about the camshaft design, this cam 2 special circle in the top of the intake and exhaust, they are closed during the compression, heat addition, and power. Now, I don't want this anymore. The internal exhaust, which is carbon monoxide, carbon dioxide, mononitride. It is a lot of gases I don't want. I want to have new fresh air. We assume it's a cycle. It means repeat itself. It became again air. But for us, we need to open now the exhaust, let this bad gases go away, then enter new fresh air and fuel and repeat the cycle. So we care about compression, heat addition, power, exhaust. We don't care about what is going on for the intake and exiting out the burned fuels. Okay, guys? So we care about the compression and last one. So let's see them again for last time. So please repeat. I repeat these 4 stages again, and please focus on the camshaft. Only focus on the camshaft design. I like the design. Look only at the camshaft, please. Look at the camshaft, how it spin, how it keep everything closed, except the 2 stages required. If let's say 4 quarters, only quarter, let's say 3 and 4. Okay, guys, did you learn something from this video?
Yeah.
So the only difference, or the major difference between the diesel cycle and the Otto cycle, heat addition was at constant volume for Otto, here at constant pressure for diesel. That's the major difference. There is another difference, guys. Can somebody tell me what the difference is?
The ignition for diesel engines is from compression or the high pressure.
Exactly. So this is a very good example, the difference between the self-ignition and spark ignition, which is we enforce it and it's naturally or happen due to high compression. That's also another perfect comparison or example for the difference between these 2 engines or these 2 design. Let's go now derive the efficiency for diesel engine. Again, eta thermal is, and it will be forever 1 minus Q low over Q high. Q low, constant volume, Q high at constant pressure for diesel engine. Q low and Q high was at constant volume for Otto cycle. So it's 1 minus CV T4 minus T1, exactly same as this one. But here is not. It's CP T3 minus T2. Make sense, guys? Make sense?
Yeah.
So here CV cancels CV. But what happened here? CB over CV is what? Can somebody tell me what is this? A specific K. Down here K. A specific heat ratio. Again, take T1 and T2 common factor. So it's 1 minus 1 over. Now we have K. And we have T4 times T4 over T1 minus 1 over T2, T3 over T2 minus 1. Correct? Actually, I take T1. I take T1. I'm sorry. I took T1 here. I take T2 here. Yes. Correct? Hello? Can you see that, guys?
Yeah.
So T2 over T1, it's V2 over V1 or V1 over V2. It's compression ratio. So we have 1 minus. We have K. This over this, it's actually 1 over R to the K minus 1. Exactly same as this guy. This guy, exactly 1 over, which is compression ratio. V1 over V2, which is down. How about T4 over T1? Isentropic. T3 over T2, constant pressure. So this constant pressure one, it can be this guy in the top here. It's R to the K minus 1 and down, I think RC. Let me see it, RC. This is RC to the K. This is R to the K. R minus 1, RC minus 1. This is the final. So T4 over T1, T4 over T1, we can replace it by, in terms of RC or RC to the K minus 1. It's actually different, but this is the final form. This is the final form of the revision. Eta thermal diesel. Sometimes I ask you for extra credit if you want to do it in the exam. So you try to do it yourself. I'll keep it you for as a homework. So what is going on here, guys? If RC, as I told you before, RC equal 1. If this RC equal 1, it means constant volume. This one became vertical like this. Constant volume. So this one supposed to go to that one, correct? Correct, guys?
Yeah.
So can you tell me how can I do that? If we put limit RC tends to 1 in eta thermal diesel. Limit of RC tends to 1 in this guy. If you put it, it will be 1 minus, forget about 1 minus. Here is 0 over 0, undefined. What should I do, guys? We can use L'Hopital, Hopital or L'Hopital rule. It means differentiate this with respect to RC, responses this with respect to RC. So we have 1 minus. So we don't care about 1 minus. 1 minus, we can take it out. We have 1 over K, RC, R to the K minus 1. Okay. Now, differentiate now. This one with respect to RC, because limit to RC, is differentiate with RC. If it's here X, differentiate with respect to X. This by itself, and this by itself. So it will be K, RC to the K minus 1. Correct, guys? And this is 0. Divide down is 1. Correct, guys? L'Hopital rule. Correct? So differentiate this with respect to RC. RC to the K minus 1. This is 0. This is RC to the K. It's K, RC minus K minus 1. Differentiate RC, it's 1 minus 0. K cancels the K. There is K here. This is K, I guess. So K cancels K. RC put it 1. This will be 1. So finally, it will be exactly same as this one. Make sense? Guys, it's not a math class, but it's okay. You do not get it, guys?
What does it say? What you crossed out? The 1 over next to the 1 over
This one?
R K minus 1. Yeah.
This
yeah.
one? Here, original was K here. So the 1 over K, it's 1 over K, correct?
Yeah.
When I differentiate this guy, it was K RC K minus 1. So it's K RC K minus 1, correct?
Yeah.
So this K, the same as this K.
Yeah. Okay.
Put RC equal 1 to the power something, it's 1. Over 1, it's 1. So 1 minus 1 over R to the K minus 1. So this K need to go with this K to be the same as this one. Because here there is no K. So when I put limit RC tends to 1, this was supposed to happen. So this one is not in the book, but I added for you for extra thinking. The math, go back to the physics. If we put RC equal tends to 1, diesel, go back to Otto cycle. It means that this cutoff compression ratio disappear, became 1, there is no extra or no constant pressure. It was here. Okay, guys? Make sense? Let's take a 10-minute break and come back at 11. So as I said in the last part, diesel engine different from Otto cycle by just the heat addition is at constant pressure, unlike Otto cycle, which was at constant volume. That's a major difference. So even this chart exactly the same, but we just write here V equal constant for Otto, P equal constant for diesel. That's it, the TS diagram, because the heat addition is at constant pressure for diesel. So let's take an example. So for diesel, if you have RC and R, and of course you have K, you can get either thermal diesel, thermal efficiency. And if you have R and K only in the Otto, you can get, because there is no RC. Here RC, there is no RC. You can get the thermal efficiency for Otto cycle. Let's take an example. Example in Otto and example in diesel. Okay, guys? Get excited? So the example says it's a problem number of 913. Problem 9. We still in section 96, 913 in the book. It's air standard cycle air. Sometimes a different gas. So all of these problems are ideal gases. Ideal gas mean, remember guys, any state P V equal RT. That's correct always at any state. 1 1 1 2 2 2 3 3 3. Only single state. U equals CVT. Internal energy CVT, assuming CV constant. If CV is not constant, it's supposed to be CV dt, integration of CV delta T from 1 to 2, for example, if you want delta U, because we care about changing U. If you want delta H, for example, constant volume, constant pressure, it's an integration CP delta T. And this is, if CV is constant, just CV delta T. CP delta T. If you want delta S for ideal gases, delta S always for ideal gases, CV ln T2 over T1 plus R ln V2 over V1, or CP ln T2 over T1 minus R ln, I think, P2 over P1. I remember this was 1 over 2. I don't remember. Something like that. So this is delta S. They are the same, exactly the same. So if you replace this to be in terms of pressure, this we're gonna get this. And of course, CP over CV, it's K, CP minus CV, it's R. These are the, we can use the tables. If you have 2, you can get 2. If you have CB and CV, you can get K. If you have CP and CV, you can get R, okay, as a midterm. So if you have given, stick to the given. If they are not given, use table A to A or A to B or A to C. It depends on the problem. So this is air. And we said, actually, this was not diesel. Okay. Before I solve this problem, let's solve another problem for diesel to make it easier for you. Or Otto. Okay. 933. 933. It was Otto. I will solve this first. Then I will go back to 913. I will tell you why. So Otto at R equal 8, compression ratio, which is V1 over V2, given equal 8. T1 was 270, 227. P1 was 95 kilopascal. Q high, 750 kilojoule per kilogram. We can use Q small if you want, which is better for this case. Required. P3, T3, W net, eta thermal, MEP, main effective pressure. This is the required. So this is, let's plot for you. This is the solution. Plot the TS diagram. It's 1, 2. So 1, 2, 3, 4. Constant volume. Constant volume. 1, 2, isentropic compression. 2, 3, heat addition. TS diagram, I like TS diagram. So this is not given. T the Q heat, Q high. This is Q low. That's small. And this minus this work net. Okay, guys? Compression, heat addition, power, heat rejection. Compression, heat addition, power, heat rejection. Compression, heat addition, power, heat rejection. So 2 heat and compression and expansion or power. So what is given here? Given here is state 1. That's good. T1, P1. It means using ideal gas law, including the RNO, I can get V1. So state 1 totally defined. I can get V1 using P, actually RT over P, or table A to A. Okay, guys? And there is no temperature change, just we are always constant for given temperature. State 2. I have R. I have R. It means I have V2. So from V1 over V2, which is R, I can get V2. So remember, so solution is state 1 completely defined. So if you have P1 and V1, T1, and R, and anything else like Q high, T high, P3, T3, anything else like this, and this, and this, you can get everything in the problem. You have a state 1, and let's say R, and anything else, let's say Q high, T3, P3, anything, T4, you can get everything in the cycle. Everything in the cycle. Let's see this one. So from T1 and P1, you get V1. So state 1 is completely defined. V1 equal R T1 over P1, or table A to A. Go to A to A, get R for A, it's 287 joule per kilogram Kelvin. You can get V1. How about state 2, isentropic with 1, and you have R, and it's ideal gas, you can get everything. How? State 2. First, you have V2, which is V1 over R. Actually, V1 over R, yeah, V2 is less. Get V1, you get V2, because R is the ratio between V1 over V2. V1 is bigger. We compress, so V2 is smaller. That's clear in PV diagram. Here is not that clear, but V1 is bigger than V2. So the volume decreases. V1 bigger than V2. And remember, V2 is constant between 2 and 3, because this is Otto engine. Unlike diesel engine, constant pressure between 2 and 3. So we have V2, guys, correct? Now, 1 and 2 is isentropic. You can get everything now. How? V2, let's say T2 over T1 equal V1 over V2 to the K minus 1. Again, K from table A to A, which is always 1.4 for air. So you can get T2. T1 is known, V1 is known, now V2 is known. From compression ratio, you can get T2. Guys, this is hard. T2 was, for this problem, I don't calculate it. It's okay, you can calculate it. It's actually higher. Yeah, it's higher. You can see here, it's higher than T1. It's compression, getting higher pressure and higher temperature, isentropically. So you can get, for example, P2. If you want P2, yes, I can get P2. P2 equal RT2 over V2. So if you want P2, if you want. How about state 3? State 3. Hi guys, state 3, what do you have? Can somebody tell me what do you have for state 3? Guys, what do we have for state 3? Hello, hello. Can you hear me, guys?
Constant volume.
Exactly, between 2 and 3 constant volume. This is Otto, constant volume. If it's diesel, constant pressure. So take B2, give it to V3 if it's diesel. Give V2 to V3 if it's Otto. So exactly, we have V3 equal V2. What else do we have? We need another independent information to have everything at state 3. So remember state postulate, we said if you have two independent intensive properties, if you have two independent intensive properties, you can get everything. So you got 2, you have everything, like V2 and V2. You can get everything, like P, U. So what else, guys, we can get? Huh? Somebody can help me? What else he gives to get T3, for example, or P3? What else he gave us? Hey, guys. What else he gave? Between 2 and 3, or at 3 at least. Huh? Q high. Q high, this is constant volume. So if you write, even if you don't know, Q minus W equals delta U. Constant volume, there is no work. Delta U, CV, this is U small. Delta T, T3 minus T2. You have T2. Yes. You have CV, table A to A. You have Q high, given. You can get T3. Correct, guys? That's it. You have 3, V3, and T3. You can get P3, for example. How? Ideal gas, which is required. So I get this and this. Make sense? Sometimes I give temperature T3. So if you have T3, substitute here, you get Q high. So I can give you Q high or T3 or P3. So for example, V3 and P3, you can get T3 and so on. If you have two independent, so 1, I can get 2, I get something in 3, but I don't know the rest. So he gave me something else, which is Q high. How about state 4, which is the last state? State 4, guys. What do we have at state 4, guys? What I know here. Somebody tell me what I know at state 4? PTV, anything? Guys, what I know about state 4, please. So between 1 and 2, constant 1 and 4, constant volume. 3 and 4, isentropic. From these two information, I can get everything at 4. 1 and 2, 1 and 4, V constant. It means V4 equal V1. So I have V4. 3 and 4, isentropic. 3 and 4, isentropic. So T3 over T4 over T3 equal V3 over V4 to the K minus 1. 3, 3, 4, 4, opposite. Here to the K minus 1. I have T3, I have V3, I have V4, I can get T4. I can get B4. The most important thing to make sure that at every state you have pressure, temperature. Temperature is the most important thing. Everything is function of temperature. You have T2, you have T1 is given already. You have T3, you have T4, you are done. If you want the work net, for example, the work net, it's just Q high minus Q low. Q high, it is CV T3 minus T2, which was already given. So CV T3 minus T2. If you have all the temperature, you are done. Q low, CV T4 minus T1. So this guy, CV T3 minus T2, which is given already. This one, CV T4 minus. Why I'm saying CV, guys, not CB? Can somebody tell me why I'm saying CV, not CP?
Because it's at constant volume.
Exactly. I'm constant volume. Volume is CV. If it's constant pressure, P, it's CP. Is it hard to remember? It's hard to remember, guys. CV, constant volume. CP, constant pressure. That's even if you don't remember, you will remember by yourself because it's constant V. Okay, guys? So you can get work net. If you try to use 3 and 4, you need to use this and this together. It means you need to say here, the work here, there is no heat. So Q minus W equal, for example, delta U, constant volume. There is no heat because this is adiabatic. You can get work. And here also Q minus W equal delta U. So if he is CV delta T, CV delta T. So this minus this is work net. If you want to use that, it's okay. It's up to you. So if you use W power minus W compression, which is CV power is T3 minus T2, bigger minus smaller, minus 4. The compression is CV also, bigger minus smaller, T2 minus T. If you simplify this, it's exactly like this. This is CV. If you simplify this and this, exactly the same equation. You will see T3 minus T2, T3 minus T2, minus T4 plus T1, minus T4 plus T1. Exactly the same. It's up to you. You can use Q high minus Q low or W power minus W compression. Make sense, guys?
Yeah.
Okay, this guy, eta thermal, it's 1 minus Q low over Q high, correct? You have Q low, CV delta T between 1 and 4. You have Q high, which is already given. You can get this. There is another way, guy. Can somebody tell me how can I get eta thermal differently? How can I get eta thermal differently, guys? Hello, hello. Can I get eta thermal differently using this guy? Only this guy, okay? Guys, can somebody tell me?
1 over, I mean, 1 minus 1 over R, K3 minus 1.
Yes. So this is a very good check for yourself that Q low is correct, which is mean W work. So if you use just R, that's perfect, correct. So if you have this problem, and I get you give all this data, even this only, and of course you get K from table A to A for air, you can get eta thermal in 1 minute. Does it take more than 1 minute, guys? Does it take more than 1 minute, guys? Tell me, please. I don't think so. So this does not take more than 1 minute, and you will see it in the exam. All the exams, this is 1 minute line. If you have compression ratio for the Otto, you can get. If you have compression ratio for the diesel, you can get, and of course cutoff volume ratio, both R and RC. Here we need only R and K. Then we need R and RC and K for diesel. So the last thing was MEP, mean effective pressure. MEP was power, which is W net, divided by V1 minus V2. We have V1, we have V2, and we have W net. Just give mean effective pressure. And this is per unit mass. If you have the mass, you can get absolute value. Okay, guys? Okay, guys? Any problems? Any question? So remember, this is called ideal gas. Do not forget this. CV delta T, Cp delta T for H, constant pressure, constant volume, delta S, and if it's isentropic, put this 0, which we simplify it P V to the K or T V to the K minus 1 and so on. This is called isentropic relation if it's 0. If it is not, you're supposed to obtain it. Okay, guys? So what we have now? We learned now Carnot cycle. We learned now Otto cycle. 2 constant volume. We learned now diesel cycle. Heat addition at constant pressure, heat rejection and constant volume. So the difference between this and this, heat addition, constant pressure, constant volume. We learned also a special cycle. What a special cycle means? A special cycle is I give you details. I give you details. For example, problem 13, which is the one I stopped it. Remember when I said I will talk about 13 after this? Hey guys, could you please open the book at problem 913? Open the textbook, problem 913. Of course, you will see 1 or maybe 2 in the final exam of this special cycle. Open problem 913, please, in the textbook. Chapter 9, problem 913. So you need to be prepared. You have the homework, you have the, actually I need to upload the homework. V4 equal V1 because it's a constant volume heat rejection. Somebody asked why V4 equal V1. Georgie? Did you know what is going on? So it's heat rejection at constant volume between 4 and 1. That's why V4 equal V1. Got it? Go back to the chart. Even in the PV diagram is better. PV diagram is better to see V4 equal V1 because it's vertical. In PV diagram, vertical mean constant volume. TS diagram, it's a little bit hard. That's why we write in a slant curve, V equal constant, P equal constant. So you need to know that. If you have a curved process, you need to write what is this, like isentropic in PV diagram, isentropic in PV diagram. But in TS diagram, no, don't write isentropic. It's vertical. I know it's isentropic. But if you have slope, like slanted, you need to write like for here, Otto cycle in TS diagram is like this. I don't need to mention that. This is TS. Of course, this is isentropic, this is isentropic. I don't need to mention. But this is V equal constant. This V equal, I need to mention that. In diesel, 1, 2, 3, 4. Here, I need to mention this is pressure equal constant, P equal constant. I don't need to mention that because it's constant entropy. If you go to PV diagram for Otto, this is Otto, this is diesel. Otto is different, like something like this. 1, 2, 3, 4. Here is opposite. I need to mention this isentropic. Isentropic. This isentropic, exactly is isentropic. Here I need to mention isentropic because it's PV diagram. I need to not mention this because it's vertical. I need to not mention this, it's vertical. I need to mention this. That's why always you will see me write isentropic here. I don't write something 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 here. I write here V equal constant, V equal constant, P equal constant, V equal constant. Here, PV diagram. Isentropic. Actually, this is wrong. 1, 2, 3, 4. This is isentropic. This is isentropic. So pressure is constant between 2 and 3. Okay, guys, make sense? Does it make sense for you? This is look like we are in airport and you're announcing the landing. So problem 913, if you read it, it's a special cycle. It means I give you all the processes, 1 to 2, 2 to 3, 3 to 1, or 3 to 4, 4 to 5, 5 to 1. I can give you all the steps. For example, from 1 to back to 1, it can be 5 processes, 4 processes, 3 processes. You need at least 3 processes to have a cycle. So he said, we have only 4 processes. It's air, 913. It was air. So you have CP, CV, you have R, you have K from table A to A. Table A to A. I don't know how many times I need to say table A to A. All we need for all of them, make sure you have temperature 1 to temperature 4. 1, T1, T2. Make sure for all of them. If you have all the temperature, you have everything. So you have air. Closed system, 4 processes. We have 4 processes. Of course, this is closed system. So Q minus W equal delta U. Q minus W equal delta U. That's it. This is the first law of thermodynamics for closed system. Here, we don't have heat, but we have work. Here, we have heat, we don't have work. Here, we don't have heat, but we have work. Here, we have heat. So usually this is 0, this is not 0. This is not 0, this is 0. Or like constant pressure. So this is P delta V, which is Q equal delta H. That's it. 4 processes. He said 1 to 2. Well, this is the, forget about this now. Start here in TS diagram, start here in PV diagram. Bottom right, bottom left. TS, bottom right. Let's do it. Which one do you guys want? Do you want the TS or PV? Let's do both. TS, PV. How PV? Where do I start, guys? PV, where? Bottom left or bottom right? Which one?
Bottom right.
Bottom right. Perfect. So here, somewhere here. State 1. How about TS? Somewhere here. Give it a little bit space. Because sometimes you have constant pressure in the back. Usually there is no constant entropy or temperature in the back. This is 1, this is 1. He said, the first one was compression, isentropic. Isentropic, how? Isentropic here. TS is easier. How can I have isentropic, guys? It's horizontal or vertical or slanted? 1 to 2 is isentropic. I was just reading the question, not the curve. Isentropic compression. It means
Slanted?
isentropic, constant entropy.
Oh, vertical.
Vertical. Perfect. This is 2. Isentropic here is slanted like this. Like what we did in the here or here. This was isentropic. Correct? 2 to 3, constant volume. Here is easier. Constant volume is what? Vertical, horizontal?
Vertical.
Vertical, exactly like Otto. Heat addition, he said, at constant volume. Here, like Otto, like this. Then he said 3 to 4, isentropic expansion. Isentropic. Here is easier. How isentropic look like? Horizontal or vertical? What? Isentropic.
Vertical.
Vertical. Perfect. Here. This is state 4, somewhere here. Expansion, it means temperature decreases, pressure decreases. So expansion means everything decreases. Expansion. Isentropic expand. This is compression, pressure build up, volume decreases. Expansion, volume increases. It very look like very same like as Otto cycle and so far. How about the last one? Pressure equal constant. It means I'm along this line. 4 is somewhere here. It's not here. It's not constant volume finally. So I need to continue this curve until I get this point. So 4 isentropic like this. Then finally pressure, I didn't need, but I will write it for you. V equal constant. Here, constant pressure, like this. This is V equal constant. This is P equal constant. Heat addition here, heat rejection there. Heat rejection there, heat addition here. Is it good, guys, or is hard or easy? It's exactly opposite to diesel cycle. Exactly. Correct? Correct?
Yeah.
So he gave us P state 1 completely. He gave T3. I like TS diagram. He gave T3. He gave B4 and B4, of course, constant volume, and P3. No, P3, no. Yes, that's what he gave. Volume constant, pressure constant, isentropics, heat rejection, that's it. This is called a special cycle. It means I'll give you details between 1 and 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, then back to 1. This is called a cycle. From 1 to 1. It can be just 1 to 2, 2 to 3, 3 to 1. Yes, it can be like this. Okay, guys? Okay. Okay, guys?
Yeah.
So what's given here? Here we have P1 and T1. Okay, you have V1. So you have, for example, P1 and T1 solution at 1. We need to make sure you have all the temperatures. If you have T1, T2, T3, T4, all the temperatures, you are fine. At 1. You have P1 and V1, T1. You can get V1. How? Ideal gas law, RT over P. You can get V1. He gives P2, actually, he gave P2 600 kilopascal. He gives the P2 600, it's given. Okay, guys? He need to give two things, only two things, like this one and this one. And the first state, P1 and T1. That's it. Like 4 information. One here, one here, one here, one here. Or 2 here, 1 here, and 1 here. That's it. So at 1 is done. At 2, I only have P2 given. But I know between 1 and 2, isentropic. It means P2 over P1 equals T2 over T1 to the K over K minus 1. So I can get T2. 1 and 2 isentropic. 1 and 2 isentropic. So I can get T2 because I have P2 and everything about 1. So I have P2 given. So I can get V3, V2. V2 is RT over P2. I can get V2. So state 2 is completed. Add 3. What I know about 3, guys, he gave me T3. Given. Or Kelvin. So make sure it's Kelvin. Everything is supposed to be Kelvin. His temperature is Kelvin. Everything is Kelvin. What else I know about 3, guys? What else, guys? What I know about 3. Look here and look there. So do you have everything about 4? Not yet. You have everything about 2? Yes. What is constant between 2 and 3?
V3 equals V2.
That's it. V3, perfect, equal V2. You can get B3, for example, which is RT over V. So state 3 is completed. State 2 completed. State 1 is completed. How about at 4? What do I know about 4, guys? Yeah, I have everything about 4. What do I know about 4? Huh? I have P4 equal 100 kilopascal, which is the same as P1. How about this one? The same pressure, it's okay. How about this one? What is this, guys? What is this? Called what? Between 3 and 4. I have everything at 3. It can help me to get 4. What is between 3 and 4? It's called what? What is a vertical line in TS diagram? Hey guys, hello.
Constant entropy.
Which is called what? Isentropic. Constant entropy. Isentropic. It means P3. So 3 and 4, isentropic. So P3 over P4 equal T3 over T4 to the K over K minus 1. Do you remember when I said I used to use this 3.5 for air? It's always 3.5 for air. 1.4 over 0.4 is 3.5 for air. I memorized it when I was in your age because I used to use it a lot. I said, that's 1.4. So it's 3.5. K over K minus 1 is always 3.5. So I can get T4 in Kelvin, of course, everything in Kelvin. Now I have all the temperatures, I have everything. What he wants the PV diagram, TS diagram, working it. Working it is easy. So working it, we need Q high and Q low. Look at Q high and Q low. Right? Q high here is what? At constant what? Constant what? Guys, Q high at constant what? Hello? Q high at constant what?
Constant volume.
So it's what? CB or a CV?
CV.
Perfect. CV delta T, which is T3 minus T2. Exactly like Otto cycle. How about kilo? Is it constant volume or constant pressure?
Pressure.
Pressure, it means
CP.
C what?
P.
CP, which is T4 minus T1, bigger minus small, always bigger minus small, to get the absolute heat. We knew the Q high is positive, but Q low is negative with respect to system. But now we care about absolute Q input and out. So W net out, just Q high minus Q low. If you want thermal efficiency, 1 minus Q low over Q high. Here, so this is required B. So A was the plot, these sketches. B was this. C, eta thermal. Guys, is this hard? This is a harder problem? Please tell me now if it is a harder problem or not. I keep fighting with my daughter to stop saying or not. They're like, Daddy, you like this or not? Stop saying that. I'm keep saying it every time. Hey guys, do you like it or not?
Yeah.
So this is how we deal with, I have another problem for diesel. It's in the lecture. Please go ahead and read it. So what about the last one, which is dual cycle? So a special cycle, I will give you details, 1 to 2, 2 to 3, 3 to 4. What happened? I give you 4 information, usually P1, T1, any two other things, P2, T3, for example. If you have 4 information in a cycle, you can have everything in a cycle. For example, O2. If you have P1, T1, R, and T3, you can get everything. Q, like last problem, Q high, you can have everything. So you need 4 information in cycle, 4 information in any cycle to get everything about the cycle. So dual cycle, it's a combined cycle between Otto and diesel. So let's repeat back what happened on Otto, for example. Otto is like this. Let's talk about PV diagram. PV diagram Otto. It's 1 to 2, 2 to 3, 3 to 4. This is Otto, correct? Okay, forget about this now. This is Otto. He said no. How about this? If we just give some heat at constant volume, let's say point X, then give some heat at constant pressure. This is called Dewel. So I give heat Q high 1, Q high 2. From 2 to X, Q high 1 at constant volume. So Q high 1 equal, for example, constant volume CV Tx minus T2. Q high 2 is CP T3 minus Tx. T3 is higher. I'm adding heat, temperature increases. So this minus this, this minus this. This is the Q high 1 and 2, which is Q high equal Q high 1 plus Q high 2. So heat addition, some part at constant volume, some part at constant pressure. Then isentropic expansion. So this is always isentropic. This is always isentropic. Compression or expansion. Compression or power. So always this is isentropic because it's adiabatic and reversible. Isentropic. Adiabatic and reversible. Isentropic. Constant entropy. Vertical in the, let's plot it in the TH diagram. We start here 1, 2, then 2 to 3, 2 to X, sorry, constant volume. X to 3, constant pressure. Isentropic from 3 to 4, constant volume at 4 to 1. So in the past, if this is completely constant volume, Otto. Constant pressure, diesel. Some part from 2 to X, constant volume. And some part at constant pressure from X to 3, constant pressure and constant volume is called Dewel. We call it Dewel. Do you know, guys, why I do that? We do that. Why we do that? We wish to go vertically from 2 to 3. But why we do that? Some materials cannot sustain at high pressure. If you keep going vertically from 2 to 3, this is huge pressure. It's too much load on the material. That's why diesel has some advantage, but Otto has advantage. Otto is more efficient if you have material can sustain or be stable at a very high pressure and temperature. So we can have high pressure and keep increasing temperature, but the pressure doesn't go too much. So if you go completely horizontal, diesel. Some part vertical, some part horizontal, Dewel. Completely vertical, Otto. Carnot, all of them have two isentropic. The Q high and Q low here, volume, constant volume. So here, constant volume. Here, they are isothermal, constant temperature. Constant volume. Constant pressure, constant volume. Especially depends on what I say. They will some part constant volume, some part constant pressure, but this is constant volume. Is it easy, guys? Is it clear now?
So wait, the graph, the PV diagram at the top represents the dual cycle?
Exactly.
Or, okay.
This part is called Dewel. If you have it only vertical, it's what? Otto. If it has only horizontal, it's called what? Diesel. If you have part vertical, part horizontal, it's called Dewel. This is the end of section 9.6. So if you open, please, in the lecture 16, page 8, I summarize all of them. We start PV diagram, bottom right, bottom right, bottom right, bottom right, bottom left, bottom left, bottom left, Otto, Diesel, Dewel, and even Brighton. Brighton is a coming lecture. We're going to discuss it in details in the coming lecture. Okay? Okay?
Yep.
So please make sure you understand. I know the exam is open book, but do not depend on that. If you don't know what's going on, you will have hard time. You have time to solve the problem, not to understand what is going on. So make sure you understand now. Make all the mistakes now. Okay? So Brighton cycle, for example, let's talk about the last one, which is Brighton, which is 9.6. This is 9.12, 9.3, 9.5. We have here 9.4 Ericsson. I dropped it. We have this, which is along everything. We have here 9.6. Here 1.8, we have Brighton. Brighton is jet engine or airplane. Exactly similar to those, but different story, of course, but at constant pressure. So this and this at constant pressure. So if you plot it, for example, TS diagram, it's 1 to 2, 2 to 3, 3 to 4, 4 to 1. So here 1 to 2, 3 to 4. This is called Brighton 9 point. We're going to repeat it in the beginning of the next lecture. This is PV diagram and this is TS diagram. Here, compression. Actually, this is isentropic compression. This is isentropic expansion. Here, constant pressure, heat addition. Constant pressure, heat rejection. So if you have two constant volume, last minute, if you have constant volume, Otto. Constant pressure, Brighton. This is volume constant, this is pressure constant. We call it diesel. Look at the PV diagram, exactly the same thing. PV diagram is something like this. So 1 to 2, isentropic. 2 to 3, heat addition at constant pressure. 3 to 4, it's isentropic. 3 to 4 isentropic, constant entropy. 4 to 1, pressure is constant, which is heat rejection. Okay, guys, any questions? We are done.